In this section, we will cover the relationships that the compressor vendor uses to determine the head produced, the efficiency, the horsepower, and the overall design for a particular compressor application. As previously mentioned, the end user's objective is to deliver a specified amount of a given gas to the process. Therefore, the data that the compressor vendor obtains is required mass flow, inlet pressure, temperature conditions, and gas composition. With this data, a compressor manufacturer will calculate the actual flow, the ideal energy required, and the horsepower to achieve that objective. The calculation for horsepower will require a specific compressor efficiency as well as compressor mechanical losses, that is, bearing friction losses, seal losses, and disc friction losses. There will be more about this in a later section. Gas characteristics are defined in this section, and useful relationships are presented to enable you to calculate various compressor requirements. Now, once the vendor obtains the data, the gas head can be calculated, and once the head and required flow are known, the impeller can be selected. The principle of impeller design is chiefly based on that of specific speed. Specific speed is defined as the ratio of speed times the square root of the actual flow divided by head raised to the 3/4 power, as depicted in the following equation. It can be seen that increasing values of specific speed will result in increasing impeller efficiencies. Therefore, having been given the required flow and head, the only source of obtaining higher specific speed for the vendor is to increase the compressor speed. This fact is very significant because while compressors have increased in efficiency over the years, the mechanical requirements have also increased in a significant way, resulting in potential reliability problems. Therefore, what I want you to understand here and to keep in mind is that the design of the impeller is a very fine balance between the performance requirements and the mechanical constraints of the components used in the compressor design. Finally, efficiency is presented in this section as a ratio of ideal head to actual head, as depicted on a typical Mollier diagram. In addition, the fan laws are presented showing how increased impeller head can be obtained via speed change in a compressor application. The objective of the end user is to deliver a specified amount of a given gas to the process. Take a look at the following figure. It shows a simplified process scheme. Note here that our objective can be best stated by the following relationship. So, the gas flow produced, seen here, must be equal to the gas flow delivered. This is the reason why most process control systems monitor pressure and install a controller to either modulate the flow via a control valve, which will change the head required by the process, or via the speed of the compressor, which will change the head produced by the compressor. The vendor then determines the head required by the process based on the parameters given by the end user on the equipment data sheet. It is very important to note that all possible sources should be used to confirm that the conditions stated on the data sheet are correct and realistic. This fact is especially true for dynamic compressors, since incorrect process conditions will impact the throughput of the compressor. In this video, we will present the relationships used to calculate the design parameters for the compressor. Note here that the same relationships are used regardless of the type of compressor, whether it is a positive displacement compressor or a dynamic compressor. Now, to achieve the client's objective, the compressor vendor must calculate the actual flow to the compressor inlet, the actual energy or head, and the work required. To calculate the actual flow, the vendor will use the following relationship. So, the volume flow rate to the compressor inlet is equal to the mass flow rate divided by the density of the gas. And the density here depends on the pressure at the section of the compressor, the temperature, the molecular weight, and the compressibility. Now, to calculate the energy or head produced by the compressor, the vendor will use the following relationship. It is the energy required to compress and deliver 1 pound of gas from the section pressure P1 to the discharge pressure P2. The mass of the gas depends on the molecular weight, the pressures, so P1 and P2, the compressibility, the inlet temperature, and the efficiency of the compressor. And finally, the work can be calculated using this last equation. So here you can see the work or the power is equal to the ideal energy times the mass flow divided by 33 thousandths times the efficiency of the compression. The gas characteristics used to determine the design parameters are defined here. They include the compressibility factor, referred to in this course with the letter Z, which accounts for the deviation from an ideal gas. The specific heats at constant pressure and volume, respectively Cp and Cv, which are the amount of heat to raise one mass of gas 1 degree. The specific heat ratio, Cp over Cv. The molecular weight, referred to in this course with Mw. And finally, the polytropic exponent, referred to with the letter N, which is used in polytropic head calculations. Recall the formula we've seen in a previous video. Now I'm going to show you some useful relationships used in compressor calculations, as well as the definitions for the constants that are used. The actual volume flow can be calculated by dividing the mass flow rate by the density of the gas. The density of any gas can be calculated using the following equation, where P is the absolute pressure expressed in psi, T is the gas temperature expressed in Fahrenheit plus 460, Z is the compressibility factor, and the value of R is seen here. The next useful relationship links the actual volume flow to the standard volume flow, as illustrated here. Recall that the standard volume flow is referenced to 60 degrees Fahrenheit and 14.7 psi. So here again, the temperature is in Fahrenheit plus 460, and the pressure is the absolute pressure expressed in psi. To calculate the brake horsepower of the compressor, you can use the following equation. So, summing the gas horsepower and the mechanical losses. The mechanical losses of a compressor include the bearing losses, the mechanical seal losses, and any other type of friction losses. The gas horsepower is calculated by multiplying the compressor head by the mass flow, then dividing it by 33,000 times the efficiency. This is for reminder the ideal gas head equations for isothermal, isentropic or adiabatic, and polytropic. Recall, as discussed previously, that polytropic head is the usual choice among compressor vendors.